For a long time, the story of the universe seemed to be settling into place. We had a model that could explain the Big Bang, the oldest light in space, the growth of galaxies, and the invisible ingredients shaping everything around us. It was not perfect, but it was powerful. Then James Webb began looking deeper than any telescope before it, and instead of making the picture simpler, it made the picture stranger. The more carefully astronomers examined the cosmos, the more it seemed that one of the most important numbers in physics refused to behave. That number is called the Hubble constant. It sounds technical, even harmless, but it describes something enormous. It measures how fast the universe is expanding right now at this moment, across the vast distances between galaxies, clusters, and every stretch of space in between. You might think there should be one clean answer. After all, the universe only expands at one actual rate. Different scientists can use different tools, different calculations, and different observations. But if the methods are sound, those methods should lead back to the same reality. Instead, modern cosmology has landed in a place that feels deeply uncomfortable. Two of the best ways we have of measuring the expansion of the universe give two different answers. Not slightly different, not close enough to ignore. Different enough to create one of the biggest debates in physics. One method begins with the earliest universe. It studies the cosmic microwave background, the ancient radiation left behind after the hot young universe cooled enough for light to travel freely. This faint afterglow acts like a snapshot of reality when everything was still incredibly young. From that early image, scientists can infer the ingredients of the universe, feed those conditions into the standard model of cosmology, and project the story forward. If the model is correct, it should predict how fast the universe ought to be expanding billions of years later. That calculation gives a value near 67 kilometers per second per megaparsec. In other words, for every vast step outward you take across the universe, galaxies should be moving away from us about 67 kilometers per second faster. The number is precise, stable, and backed by extraordinary data. The second method does not begin with the infant cosmos. It begins much closer to home. Instead of modeling the early universe and running the equations forward, astronomers measure the modern universe directly, building distance step by step through carefully calibrated objects that act as cosmic markers. This is known as the distance ladder. First come keyfied variable stars, stars that pulse in brightness at a rate connected to their true luminosity. Measure the rhythm of that pulse, compare it to how bright the star appears from Earth, and you can estimate distance. From there, astronomers move outward to galaxies containing both Cephids and Type Ia supernova. Those supernovae explode with a very predictable brightness, which makes them incredibly useful. Once you calibrate them nearby, you can use them to measure galaxies much farther away across intergalactic space. When researchers using this method calculate the Hubble constant, they do not get 67. They get something close to 73. That difference may sound small to anyone outside astrophysics, but in this field, it is a gulf. It is large enough to suggest something fundamental may be missing. This disagreement became known as the Hubble tension, and at first, many scientists assumed the tension would eventually disappear. That is how science often works. New measurements arrive, a hidden bias is found. An instrument limit is corrected, and the pieces finally snap together into a cleaner picture. The most comforting explanation was that the local measurements were being distorted by ordinary observational problems. Maybe some of the stars being used as distance markers were affected by dust. Maybe nearby starlight was blending together. Maybe the telescope images were not separating crowded regions cleanly enough. That explanation mattered because it meant the universe itself was probably fine. The model would survive, the equations would remain intact, and the disagreement would be blamed on technique. In other words, the crisis would not be about reality, it would simply be about measurement. And for a while, that seemed plausible. The Hubble Space Telescope, as revolutionary as it was, still had limits. When it looked into dense stellar environments, especially in bright spiral galaxies, neighboring stars could contaminate the signal. That contamination could make crucial Cepheid stars appear brighter than they really were. If a star appears brighter than expected, astronomers may think it is closer than it truly is. If the inferred distances shrink, the expansion rate rises. So if crowding was skewing the data, then improving the sharpness of those observations should reduce the measured expansion rate and ease the tension. That was exactly why so many eyes turned toward James Webb. Webb was not just another telescope. It was built to see the universe with extraordinary sensitivity and infrared light, cutting through dust and resolving structures with a precision that promised to test the entire argument. If the local distance ladder had been misleading astronomers, Webb had the power to reveal it. Its mirror was larger, its instruments sharper, and its ability to peer through obscuring material made it the ideal tool to revisit the stars at the center of this cosmic disagreement. The expectation in much of the field was clear. Webb would take a second look at the Cephids, correct the hidden errors, and bring the locally measured value downward. The Hubble tension would fade, the standard model would breathe easier, and cosmology would move forward with a repaired framework. But when the data arrived, that is not what happened. Webb did not expose a simple mistake. It did not quietly rescue the old prediction. Instead, it reinforced the measurements that had been causing discomfort for years. The local universe still seemed to be expanding faster than expected. That result changed the emotional temperature of the entire debate. A discrepancy that had once sounded like a technical nuisance now looked harder to dismiss. Better data had not removed the problem. Better data had sharpened it. And once that happens in science, the conversation becomes much more serious. Because now the uncomfortable question is no longer whether one telescope made a small mistake. The question becomes whether our model of the universe is missing something real. If two strong methods disagree and cleaner observations fail to reconcile them, perhaps the disagreement is pointing toward new physics. That possibility is what makes this issue so fascinating. The standard model of cosmology is not some fragile idea hanging by a thread. It has explained an astonishing range of observations with remarkable success. It describes the structure of the cosmos on scales so large, they almost defy imagination. It accounts for the cosmic microwave background. It explains the broad distribution of matter across space. It fits the abundances of the lightest elements forged in the early universe. It gives cosmologists a framework that has worked so well, for so long, that challenging it is not taken lightly. And yet, this is exactly why the Hubble tension matters. When a model succeeds everywhere else, a stubborn mismatch becomes even more important, not less. A contradiction inside a strong theory is often more revealing than a contradiction inside a weak one because it hints at a hidden boundary. It suggests there may be some ingredient that only becomes visible when our measurements become precise enough. Maybe the early universe behaved differently than we assume. Maybe the expansion history of space contains a missing chapter. Maybe some unseen component briefly altered the cosmic story before fading from view. Ideas like early dark energy emerged from exactly that kind of thinking. The concept is speculative, but the logic is elegant. If the young universe experienced a temporary burst of extra energy, it could change the later expansion prediction without completely destroying the many things the standard model still explains. Whether that idea is right remains unknown. But the fact that such ideas are now taken seriously tells you everything about the moment cosmology is living through. This is not just about one number anymore. It's about whether the universe has been more complicated all along than our best model allows. The tension becomes even more dramatic when you remember what is at stake. Change the expansion rate, and you start changing the age of the universe, the timing of the first stars, the growth history of galaxies, and the balance between the invisible forces that shape cosmic evolution. This is why some scientists speak so carefully when discussing the problem. They are not eager to claim a revolution too early. But they also know that if the discrepancy survives every observational test, then the safest explanation may become the hardest one. Our map of the universe is incomplete. What makes James Webb so important in this story is not simply that it found something strange, it is that it arrived as a referee. It came into the debate with the power to settle a long-running argument, and instead of closing the case, it made the argument more difficult. That is the atmosphere surrounding modern cosmology right now. The best data in history is not delivering peace, it is delivering pressure. Pressure on assumptions, pressure on methods, pressure on a model that still works brilliantly, but may no longer explain everything it was once trusted to explain. And this is only the beginning of the story, because the Hubble tension is not the only place where Webb has been forcing astronomers to look again. As the telescope kept observing, it began uncovering objects in the early universe that would push the crisis even further. But Webb's challenge to cosmology did not stop with the expansion rate. Almost as soon as its first deep observations arrived, astronomers began noticing something else that felt equally unsettling. The early universe did not just look active. In some cases, it looked far too mature. According to the standard picture, the universe's first galaxies should have been small, messy, and still under construction. These systems were expected to appear as faint building blocks, slowly merging and growing over time. That is the kind of youthful chaos astronomers were prepared to find. Instead, Webb began revealing galaxies that seemed surprisingly massive, surprisingly bright, and in some cases already structured only a few 100 million years after the Big Bang. These were not the tiny cosmic seedlings many researchers had imagined. They looked more like systems already growing up too fast. That immediately raised a disturbing question. How could galaxies gather so much mass so early? Star formation is not supposed to be perfectly efficient. Gas heats up, radiation pushes material away, and violent feedback from newborn stars disrupts future growth. In normal models, galaxy building should be difficult. Yet some of Webb's earliest candidates seem to be doing the impossible. They appeared to contain enormous numbers of stars at an age when the universe was barely getting started. In simple terms, they looked as though cosmic history had accelerated far beyond what standard cosmology seemed ready to allow. For a brief moment, the reaction was close to shock. If those first estimates were correct, then galaxy formation models were missing something huge. Either stars could form far faster than expected, or the universe was assembling structure in a way current theory did not properly describe. The reason this mattered so much is that galaxies are not random decorations sprinkled through space. Their formation depends on the deep architecture of cosmology itself. Its dark matter, gravity, cooling gas, and the expansion history of the universe all shape when galaxies appear. How quickly they grow, and what forms they take. So when Webb seemed to uncover giant galaxies in the distant past, the discovery did not remain trapped inside astrophysics. It pushed against the foundations of the standard model. A universe producing large, luminous systems too early would force scientists to reconsider the timeline of structure formation itself. Some researchers began stress testing the model immediately. They asked a brutal but necessary question. If we take these galaxy candidates at face value, can the standard cosmological framework still survive? The answer was uncomfortable. In several cases, the observations pressed disturbingly close to the theoretical limit. To make the numbers work, galaxies would have needed to convert an absurd fraction of their available matter into stars. Not 10%, not even something merely optimistic. In the most alarming interpretations, the efficiency had to become so extreme that nearly every useful atom seemed to be ending up in starlight. That is not how the universe usually behaves. Real astrophysical systems waste energy, lose gas, and collide with messy environmental limits. They are not perfect machines. So when early Webb results seemed to imply near-perfect productivity, astronomers had to consider whether something about the interpretation itself was going wrong. And that is where the story took a fascinating turn. As more teams studied the data carefully, it became clear that brightness alone had been telling a misleading story. Some of these distant objects were not simply massive galaxies overflowing with stars. Something else inside them was helping create the illusion. Many of the strangest sources belonged to a population now nicknamed little red dots. These objects were compact, red, and unexpectedly intense. At first glance, they looked like galaxies that had somehow built enormous stellar populations absurdly early. But later analysis suggested that their brightness had another source. At the heart of many little red dots were actively feeding black holes. Gas spiraling inward toward those black holes heats to extraordinary temperatures, releasing vast amounts of light. Seen from billions of light years away, that glare can blend with starlight and make a galaxy seem heavier than it actually is. In other words, some of the apparent crisis came from cosmic imposters. Webb was seeing real objects, but our first interpretation exaggerated how much of their brightness came from stars. The telescope had not been wrong. The universe had simply been more deceptive and more interesting than the first headline suggested. This was a crucial correction because it prevented cosmology from spiraling into premature catastrophe. Once the little red dots were treated more carefully, several of the most dramatic mass estimates came down. Some of the galaxies that looked wildly impossible started fitting more comfortably inside the broad limits of existing theory.
But the tension did not disappear completely. That is what makes this chapter so important. Even after removing the most misleading cases, astronomers were still left with an early universe that looked highly efficient, highly productive, and in some places just a little too advanced for comfort. So the narrative shifted from total crisis to persistent strain. Webb had not killed the standard model with early galaxies, but it had forced scientists to confront a cosmos that may have been forming stars faster, organizing matter earlier, and producing mature-losing systems sooner than many theoretical expectations preferred. That distinction matters. Science is rarely overturned by one cinematic discovery that shatters everything overnight. More often, pressure builds gradually. First one, observation, looks strange. Then a correction reduces the drama, but leaves behind a residue of unease. Then other observations arrive and reveal the same pattern from different directions, and Webb kept supplying exactly that kind of pressure. Some teams reported surprisingly ordered structures at unexpectedly early times, including galaxies showing signs of disks and spiral-like organization that was difficult to square with a young universe thought to be dominated by frequent mergers, turbulence, and violent instability. A graceful spiral galaxy requires time. It usually suggests that matter settled into a relatively stable rotating system, instead of being constantly torn apart by collisions. Finding such order too early does not instantly break cosmology, but it does force theorists to ask how nature became so organized so quickly. At the same time, other Webb studies seem to show the opposite. Many early galaxies appeared chaotic, clumpy, and turbulent. Exactly the kind of adolescence theory expected, that created a more subtle puzzle. The early universe now seemed capable of producing both cosmic disorder and surprising maturity at once. That combination is harder to explain than either picture alone. A uniformly chaotic early universe would be easy to accept. A uniformly mature one would at least point toward a clear revision. But a universe containing both extremes suggests something richer is happening inside the processes of early galaxy assembly. And then there was another strange detail: shape. Some analyses suggested that a number of young galaxies looked unusually elongated, stretched into cigar-like forms rather than the more familiar structures expected from standard cold dark matter simulations. That may sound minor, but in cosmology, shape can be a deep clue. The reason is simple. Dark matter is not merely background scenery. It acts like the hidden scaffolding around which visible matter gathers. If galaxies are repeatedly forming in shapes that match alternative dark matter behavior better than the cold dark matter picture predicts, then the consequences could reach far beyond galaxy aesthetics. Change dark matter, and you change clustering. You change halo formation. You change the distribution of small galaxies around larger ones. You change how matter assembled over cosmic time. So even when a Webb anomaly seems local or visual at first, it can quickly become a question about the entire architecture of reality. This is why the telescope has created such a peculiar emotional atmosphere in astronomy. Webb often does not deliver clean revolutions. It delivers uncomfortable maybes. A dramatic result appears, then gets softened, then remains suggestive. The crisis shrinks, but it never quite disappears. The uncertainty survives in a sharper form. And in some ways, that is even more scientifically dangerous. A false alarm is easy to dismiss. A total contradiction is easy to recognize. But a result that partly fits and partly resists the model can linger for years, forcing theory and observation into a slow, relentless negotiation. This brings us back to the central theme of the Webb era. The telescope is not merely showing us prettier images of old ideas. It is testing how much pressure those ideas can withstand. Every distant galaxy, every unexpectedly bright source, every structured system at an early age adds weight to that test. The standard model has not failed. That point matters. It still explains an extraordinary amount of what we see. But with every new observation, the burden grows heavier. Cosmologists are no longer asking only whether the model works. They are asking where it bends, where it strains, and where it may finally give way. And all of this is happening while the Hubble tension remains unresolved in the background, refusing to go away. That is what makes the moment feel so charged. Webb is not presenting one isolated anomaly. It is revealing a universe where multiple threads of discomfort may be pointing toward the same deeper omission. By now, the question is bigger than whether one telescope found surprising objects. The real question is whether we are approaching the edge of a cosmological framework that has been astonishingly successful, but perhaps not complete. And that is where the story becomes even more consequential. Because once astronomers begin suspecting that several tensions may be connected, the conversation changes completely. The Hubble constant, early galaxy growth, dark matter behavior, and large-scale structure stop looking like separate technical disputes. They begin to resemble different symptoms of a single unfinished understanding of the cosmos. This is where cosmology becomes truly fascinating, because the standard model is not collapsing in front of us. It is doing something more unsettling. It is continuing to explain a huge amount of the universe with stunning precision, while leaving behind a handful of stubborn cracks. Those cracks matter because they appear in places that are too important to ignore. The expansion rate of the universe, the pace of early galaxy growth, the possible behavior of dark matter, and the distribution of matter across space all touch the deepest assumptions in modern cosmology. If one of those tensions existed by itself, scientists could treat it as an isolated problem. But when several different observations begin pressing on the same framework at once, the possibility becomes much harder to dismiss. Maybe these are not separate anomalies. Maybe they are connected. One of those quieter cracks is known as the S8 tension. It does not attract the same public attention as the Hubble tension, but among cosmologists, it has been watched carefully. It concerns how clumpy matter appears to be across the universe on very large scales. According to the standard model, matter should cluster with a certain strength over cosmic time. But when astronomers try to measure that clumpiness directly through gravitational lensing and galaxy surveys, they often find slightly less structure than the model predicts. Not dramatically less, just persistently less. That may sound like a minor disagreement, but cosmology is built from small differences that accumulate into enormous consequences. If the universe is expanding differently than expected, and matter is clustering differently than expected, then both signals may be pointing toward the same hidden ingredient. This is the reason some physicists have become more willing to entertain ideas that once felt too speculative. Not because they want the standard model to fail, but because the pressure is now coming from multiple directions, and when that happens, theory has to become more imaginative. One option is that dark energy, the mysterious agent driving the accelerated expansion of the universe, may not be as simple as we assumed. In the standard model, dark energy behaves like a constant property of space itself. It does not change, it does not evolve. It simply persists. But what if that assumption is too neat? What if dark energy had a more dynamic history? Stronger in one era, weaker in another, briefly altering the expansion of the universe before settling into the calmer form we infer today. That would change far more than a single number. Another possibility is that dark matter may not behave exactly like the cold, slow-moving substance built into standard cosmology. Cold dark matter has been extremely successful, but if its particles are lighter, warmer, or wave-like in their behavior, the structure of the universe could emerge differently. That would matter immediately for Webb's observations, the shapes of galaxies, the timing of their growth, the smoothness of large cosmic filaments, and even the abundance of small systems around larger ones all depend on the hidden scaffolding dark matter provides. Change the scaffolding, and everything above it changes too. There are also more radical possibilities. Perhaps some early field or particle existed in the young universe, and briefly influenced how matter and radiation evolved. Perhaps there was an extra phase in cosmic history that left only indirect fingerprints. Perhaps our equations smooth over behavior that reality never simplified. What makes this moment so electric is that none of those ideas can be accepted just because they sound elegant. They have to survive the brutality of observation. They must match the microwave background, galaxy clustering, lensing data, supernova measurements, and now the increasingly detailed universe that Webb keeps revealing. That is why the coming decade matters so much. Cosmology is entering a period where multiple major observatories will test the same questions from different angles. If the tensions disappear, the standard model survives stronger than before. If they remained, the case for new physics becomes much harder to escape. The Nancy Grace Roman Space Telescope will survey huge regions of space with a scale and clarity designed to probe dark energy and cosmic expansion. Euclid is already mapping the geometry of the universe. Gaia continues, refining stellar distances, Future microwave background surveys will sharpen the early universe side of the argument. Each mission acts like a different witness testifying about the same crime scene. One measures nearby stars, another measures ancient radiation, another tracks how gravity bends light across billions of light, another follows the distribution of galaxies through cosmic time. If their stories converge, the verdict becomes far more powerful. And that is why James Webb's role is so remarkable. Webb was not designed simply to produce beautiful images. Though it has done that brilliantly, it has become a pressure test for cosmology itself, exposing places where our confidence was real, and places where that confidence may have outrun the evidence. There is something deeply human about that. We like to imagine science moving smoothly forward, each new instrument filling in the blanks of a picture we already understand. But history rarely works that way. Often the best instruments do not just answer old questions. They reveal that the old questions were incomplete. That has happened before in cosmology. There was a time when measurements implied that the universe might be younger than some of the stars inside it. That contradiction looked absurd, but it did not end cosmology. It opened the door to a missing ingredient, dark energy. That changed the entire map. So today's tensions may be serving the same role. They may feel like cracks, but cracks are often where new understanding begins. A mismatch between theory and observation is not a failure of science. It is usually the first sign that reality is larger than the model we built to describe it. And if that is true, then we may be living in one of the most important scientific transitions in decades. Not because everything we know is wrong, but because so much of what we know may be incomplete. The framework still stands. We are simply starting to see the rooms it never included. That distinction is crucial. The standard model of cosmology remains one of the greatest intellectual achievements in modern science. It predicted and explained more than almost any rival idea ever proposed. But great theories are not abandoned because they are useless. They are revised because they were useful enough to expose their own limits. James Webb may ultimately be remembered not as the telescope that destroyed cosmology, but as the telescope that revealed where cosmology had become too comfortable. It forced astronomers to revisit assumptions that had seemed secure, and it did so using observations too sharp, too deep, and too persistent to wave away. That is why the phrase, "we may have misunderstood the universe," carries so much weight. It does not mean everything is chaos. It means the universe is still more subtle than our current equations capture. It means our measurements have become precise enough to detect the edges of our own understanding. And there is something almost poetic about that. On a small planet, around an ordinary star, inside one galaxy, among hundreds of billions, a species made of fragile biology has built mirrors powerful enough to detect contradictions in the structure of the cosmos. That is not confusion. That is progress at its highest level. We are not watching science fail. We are watching science arrive at a boundary where old explanations still work, but not completely. A boundary where every new observation has the potential to confirm the model, revise the model, or reveal something no one had the imagination to predict. Somewhere between the first light of the universe and the galaxies we see today, something may have happened that our best framework still does not fully capture. Maybe it was dark energy. Maybe it was dark matter. Maybe it was an early cosmic event whose fingerprints only now are becoming visible. And until that question is answered, the universe remains unfinished in the deepest possible sense. Not unfinished in itself, but unfinished in our description of it. The cosmos is still there, coherent and real, while our map struggles to keep pace with what better instruments are now allowing us to see. That may be the real legacy of James Webb. It did not just show us farther distances. It showed us the cost of thinking we were closer to the final answer than we really were. It turned certainty into curiosity again. And in science, that is often where the next revolution begins. So the story is not that the universe broke. The story is that our confidence met better evidence. And when that happens, the honest response is not panic. It is attention. Because somewhere inside these tensions, these mismatches, and these strange early galaxies, a deeper version of cosmology may already be waiting.